Hello everyone, thanks for watching this video. I'm happy to share my research with you here online. And I am a second-year master student from Tsinghua University, China. My topic is control reconfiguration of cyber-physical systems for improved performance via reverse engineering and accelerated first-order algorithms. My talk are divided into 4 parts. First, I'll start from the introduction. Cyber-physical systems have significant impacts on the society, economy, and environment, since they are decisive in supporting fundamental infrastructures and smart applications. And some CPS requires better control, for example, smart grid. It is predicted that renewable energy proportion can reach 30% by 2030 in the US. And we know that supply side and demand side must match in real time. And therefore, better control is required to attenuate large fluctuations caused by renewable energy quickly. And for mobile robots and automatic vehicles, they require more safety and reliability. And one way to achieve this is to rebuild a new controller. And we can replace the original control to a new control by implementing the state-of-the-art technologies. This can achieve the best results, for example, like photovoltaic systems. However, it can be impractical for those large existing systems like smart grid and can also have high investment. Another way is to redesign control by adding an extra part to the original control. And the red dashed part are the redesigned control we refer to here. And what is reverse engineering? It seeks a proper optimization problem being solved by given dynamic equations. Normally, we have an optimization problem, like we want to maximize or minimize our objective function, and we try to solve it using some sort of algorithm. And reverse engineering is vice versa. We start from algorithm and we find the optimization problem it actually solves. And what is forward engineering? It means to solve a given problem. So starting from algorithm, we find the optimization problem, and then we solve it again using other algorithms. And the reason we are using reverse engineering is because it provides the insight for us to redesign for optimality. And there are works use reverse engineering to improve economic efficiency, but the work to improve system dynamics is still lacking. And our framework here is to use the reverse and forward engineering by starting from the system dynamics existing control to find the optimization problems it actually solves. And then we apply accelerated algorithm to solve the optimization problems again, and we can obtain system dynamics and existing control plus some extra dynamics. And this part, extra dynamics, are able to improve the convergence rate and improve system performance. Part 2, our target systems. Here, we carefully define the system class O as our target system. For linear time invariant LTI system, xk plus 1 equals to AXK plus CWK. If it belongs to class O, if it is a gradient descent algorithm to solve minimize fx. That is to say, this equation can be written in the form as xk plus 1 equals to xk minus p times gradient fx. We have our theory 1. A system belongs to class O if and only if the 3 conditions are satisfied. And there are several examples, like multi-agent consensus algorithm, primal internet congestion control algorithm, and HVAC system control. They are examples that belong to class O. And here is the most important part, the redesign methodologies. For systems in class O, it can be reverse engineered as gradient descent algorithm to solve unconstrained convex optimization problem. And then it is natural to apply faster algorithm to solve this problem, which can result in a redesigned system formula with improved performance. Faster algorithms to solve unconstrained convex optimization problems are a lot. For example, like second-order methods like Newton's method. It has fast convergence rate. However, it requires the computation of a matrix inverse here, which means global communication among agents are required. This will make the implementation complicated and costly, and therefore our focus here are first-order methods. By taking history information, the convergence rate is able to be improved. For example, heavy ball method and accelerated gradient descent algorithms. By combining with those accelerated first-order method and the reverse engineering technique, we can obtain the reconfiguration control structure. First, we reverse engineer a given dynamical system for solving an unconstrained optimization problem. And secondly, we apply accelerated gradient descent or heavy ball method to solve the optimization problem obtained in step 1. And finally, by rearranging the redesigned system and comparing it with the original one, we can obtain the extra dynamics and achieve redesign purpose. And next, let's look at the convergence rate when applying those different methods. And this is the original system. Its convergence rate is listed below. And when the function obtained by reverse engineering belongs to this class, Lipschitz continuous, and we can see that when the convergence rate is always faster when applying HD than the original one. And if the class obtained by reverse engineering belongs to this class, Lipschitz continuous and strongly convex. And when applying HB methods, the convergence rate is better than the original one or than applying HD. And part 4 will visit those 3 examples we mentioned before. Multi-agent consensus algorithm. It refers to redesigning the existing control. And the primal internet congestion control algorithm. Here we are redesigning closed-loop control. And the third example, HVAC system control, we are redesigning control input. We start from the original algorithms here. First, we do reverse engineering to find the problem it actually solves. And then we do acceleration by applying heavy ball method or accelerated gradient descent algorithm. And finally, by comparing this formula and the original one, we are able to find the extra dynamics delta UK. So for heavy ball method, extra dynamics is beta times xk minus xk minus 1. And for HD method, delta UK can be found as this. And this is a simple 6-agent case simulation result. As we can see that those solid lines are those using our control method, and it converges faster, much faster than the best ones. The first sub-figure is applying HB method, and the second sub-figure is applying HD method. And our second example, we're using the same reconfiguration steps. First, we starting from the algorithm and combine those 4 equations and rearrange them as this. And then we reverse engineering to find the optimization problem it actually solves. And then do acceleration and implementation by finding the extra dynamics delta UIK. So for accelerated gradient descent algorithm, delta UIK is like this. And for heavy ball method, delta UIK is this. Beta times xik minus xik minus 1. And for a 2-link network shared by 3 users, the simulation result is like this. And again, those solid lines are the results applying HB method and HD method, and the dotted lines are the original dynamics. As we can see, those solid lines converge much faster than those dotted lines. Third case, HVAC system control. And we follow the same reconfiguration steps. First, we do reverse engineering, then acceleration, and finally implementation. And we can obtain the extra dynamics. For HD method, it is like this. And for HB method, extra dynamics is written as this. And the picture 7 is the simulation result of a 3-room building with an HVAC system. The blue dashed line is the temperature setting from the building manager to fulfill user comfort. They are different in 3 rooms. And the first column are temperature dynamics comparison for original dynamics and for applying HB method. And the second column are for original dynamics and HD method. And we can see from those 6 sub-figures, originals always converges faster than the risk lines, and original are the accelerated dynamics. So that is to say that our redesigned accelerations can fit the temperature setting much better than the original dynamics. This proves the effectiveness of our method. That's all.
Thanks for your listening. If you have any questions, suggestions, feel free to contact me. You can either leave a comment below or you can drop me an email. I would be more than happy to answer it. Thank you very much.